All right, so this is part 2 of L'Hopital rules. So what I want to talk about here first is 2 other types of indeterminate forms. One of them is infinity minus infinity. Well, why is that indeterminate? The reason that's indeterminate is what if you have just exactly the same infinity? You take one, you subtract the other, you get 0. But what if this infinity was just 1 bigger than this infinity? Well, then you'd get 1. And what if your second infinity was like way bigger than the first? Then you'd get negative infinity, and so on. So this is an indeterminate form because those infinities don't have to be the same thing. Infinity times 0 is also indeterminate because let's say I have something like x times 1 over x as x approaches infinity. Well, if x approaches infinity, I have infinity times 1 over infinity, which is infinity times 0, but this goes to 1. Whereas what if I had a giant infinity, like if I had x squared times 1 over x as x goes to infinity, then I'd have a giant infinity here and then kind of a regular 0 here. This is bigger than that. This goes to infinity. And basically, this is indeterminate because it depends on the strength of the infinity and the strength of the 0. If this is a giant infinity, and this is just kind of moseying towards 0, taking its time, it's going to get very big. But if 0 is really close to 0, and this is heading towards infinity, but it's kind of taking its time, then you might go towards 0. And it just kind of all depends, so it's an indeterminate form. Well, these 2 indeterminate forms are not L'Hopital forms. What you may remember from before is L'Hopital is only when you have fractions that go to infinity over infinity or 0 over 0. So what we do with these new indeterminate forms is we just make them look like this, and then I know what to do. So take this one. We've got the limit as x approaches 0 from the right of cosecant x times ln x plus 1. If I were to plug in 0, kind of, sort of, I get 1 over sine 0. Times ln of 1. 1 over sine 0 is like 1 over 0. ln 1 is 0. 1 divided by 0, if 0 is a limit, goes toward infinity. So I have 1 over 0 times 0, which is kind of like infinity times 0. And that's an indeterminate form. But this isn't a fraction. It's not infinity over infinity or 0 over 0. So I can't do L'Hopital yet. But cosecant can be rewritten as 1 over sine. So if I use that idea, I now have the limit as x approaches 0 of ln x plus 1 divided by the sine of x. And so since that's the case, now when I go to plug in 0, I have ln 1, which is 0, over sine of 0, which is 0, and that's a L'Hopital form. So I'm going to do L'Hopital to get from here to the next line and say that now I have the limit as x approaches 0 of the derivative of the top divided by the derivative of the bottom. And when I go to plug in 0 now, I have 1 over 1 divided by the cosine of 0, which is 1, and I get a big old answer of 1. So long story short, if you have another indeterminate form, just make it look like L'Hopital and you're set. So then we're going to come over here to this guy, do the same exact thing. When I plug in 0, I get 0. The ln of 0 doesn't exist, but the ln as x approaches 0 goes to negative infinity. So I have another infinity times 0, but this one's not as easy to turn into a fraction. So what we have to do is we have to get creative. So I'm going to write it like this. The limit as x approaches 0 of ln x divided by 1 over x. Is this and this, are those equivalent? Yes, because if I do keep switch flip, ln x times x over 1 is x ln x. So all I've done here is just rewrite it. And now when I plug in 0, ln of 0 is kind of sort of negative infinity, and 1 over 0 goes to infinity. This is a L'Hopital form. So now I can do L'Hopital and take the derivative of the top and the bottom. So the derivative of ln x is 1 over x. The derivative of 1 over x is negative 1 over x squared. I'm going to simplify this before I evaluate it to make my life a little bit easier. So 1 over x times negative x squared over 1, keep switch flip, just becomes negative x. And the limit as x approaches 0 of negative x is 0. All right, moving on to the next two, just two small ones here. x goes to 0. For this, I've got 1 over 0 minus 1 over 0, which is infinity minus infinity. That's another indeterminate form. Well, right now, L'Hopital only works if I have one fraction that goes to infinity over infinity, or 0 over 0. So I just need to make it look like one fraction. How do I turn two fractions into one? With a common denominator, of course. So I'm going to get a common denominator here. It'll make this the limit as x approaches 0 of x minus sine x all over x sine x. So if I do that and I plug in 0, I get 0 minus 0 over 0 times 0, which is 0 over 0. So now I can do L'Hopital. So here I just got a common denominator, denom, and then from here to here, I'm going to do L'Hopital. So when I do L'Hopital, I take the derivative of the top, the derivative of the bottom. So the top is going to be 1 minus cosine x. The bottom requires a product rule, so the first times the derivative of the second, x times cosine x, plus the second times the derivative of the first, sine x times 1. Now when I plug in 0, I get 1 minus 1 over 0 plus 0, which is 0 over 0. Got to do L'Hopital again. So now when I do L'Hopital one more time, I have the limit as x approaches 0. The derivative of the top is going to be sine x. And the derivative of the bottom is going to be a product rule. The first times the derivative of the second, plus the second times the derivative of the first, plus the derivative of sine, which is cosine. And now when I plug in 0, my numerator is 0, and my denominator is 0 plus 1 plus 1, which is 0 over 2, which is 0. So this limit goes to 0. All right, I want you to try the next limit on your own, and then we'll come back and go over it together. All right, hopefully you did pause it. On this next one, it's a lot like example 3 because I have two fractions and I need to turn them into 1. So step 1 is plug that 1 in to both of these fractions. You get 1 over 0 minus 1 over 0, which is infinity minus infinity. So I have to get this into one fraction. So then what I did next is I said, all right, fine. If I need one fraction, I'm going to get myself a common denominator. This guy gets multiplied by x minus 1. That guy gets multiplied by ln x. And this is my common denominator. But when I plug in 1 now, I have 1 minus 1 minus 0 over 0 times 0. So I have 0 over 0 again, which means I get to do L'Hopital. So when I do L'Hopital, I get the purple stuff. Ignore the green for half a second. When I do L'Hopital, my derivative is the stuff inside the parentheses. I needed a product rule on the bottom. But then when I looked at my derivative over my derivative, they both had a 1 over x. I really didn't like the complex fraction, so I distributed an x to the top and to the bottom, which made it look like this. X minus 1 over x minus 1 plus x ln x. When I plug 1 into there, I still get 0 over 0, so I got to do L'Hopital one more time. So then when I do L'Hopital one more time, the derivative of the top is just 1. The derivative of the bottom involves a product rule. Now when I plug in 1, I get 1 over 2, which is 1/2. All right, one more page. This one's really interesting now. When you have 1 to the infinity or 0 to the 0, those are both indeterminate. The reason 1 to the infinity is indeterminate is because this isn't a real 1. It's something close to 1. So if I take a number less than 1 and multiply it by itself a bazillion times, it's going to shrink. But if I take something slightly over 1 and multiply it by itself a bajillion times, it's going to grow. And everything in between can happen as well. 0 to the 0 is indeterminate because 0 to anything should be 0, but anything to 0 should be 1. So what the heck does that mean? I don't know. If you get either of these two forms, then we have to follow these steps. And I'm going to walk you through them, but the steps are up here as kind of a reference. So when I come down here, let's see what happens. Let's take us to full screen here. So if I look at this first one, let's write in red. If I take a look at this first one, I have 1 plus 1 over x to the x as x goes to infinity. So if I were to plug infinity into here, I'd have 1 plus 1 over infinity to the infinity. And that's going to be like 1 plus 0 to the infinity, which is 1 to the infinity. This is an indeterminate form. Well, what we do next is kind of unique. We say, you know what? I think this has an answer. I think it has a limit, and I'm going to call it L. And I'm just going to say this has a limit. I'm going to call that limit L. I'm going to put it there. Okay, that's fine and good. What do I do next? Well, you know what I do next is the same thing I wish I could do every second of every day. You just make a log come out of nowhere. Because when you don't know what else to do, what better than to create a log where none existed in the first place? So I'm going to take the ln of both sides. So now this is the limit as x approaches infinity of ln 1 plus 1 over x to the x equals ln L. Okay, Mrs. Bibber, why is that helpful? Why are logarithms helpful? Well, because now I can take this x and I can bring it down in front of the ln. Ooh, right down there. Okay, Mrs. Bibber, still not helpful, but look now, I have a product. And as x goes to infinity, this is infinity times ln 1 plus, technically as x goes to infinity, that'd be 0. So infinity times ln 1 is infinity times 0, which is indeterminate. All right, I turned one indeterminate into another, but this one I know how to make into a fraction. So now I'm going to take this thing right here and turn it into a fraction. And I'm going to write x approaches infinity, and this is going to be ln 1 plus 1 over x over 1 over x, which is equivalent to that guy. Now when I plug in infinity, I have ln 1. Oh, well, actually, I probably shouldn't put it there, but that's okay. I have ln 1 over 1 over infinity, which is 0 over 0. Yay, I can do L'Hopital now. So I take this guy, and I take the derivative of the top, and I take the derivative of the bottom. The derivative of the top is the derivative of the end over the end. So the derivative of 1 plus 1 over x is going to be negative x to the negative 2 over 1 plus x to the negative 1. The derivative of the end, this guy, over the end right here. And the derivative of 1 over x is negative x to the negative 2. So if I keep switch flip this, it's really dividing by this is the same as multiplying by 1 over that, which cancels these guys and makes this the limit as x approaches infinity of 1 over 1 plus x to the negative 1, which is 1 over x, which is going to be, as x approaches infinity, 1 over 1 plus 1 over infinity, which is 1. Don't box that in, though. This was all set equal to L, remember, which means now it's all set equal to ln L, which means this turned into that, turned into that, turned into that, turned into this, but this equals ln L, where L is the limit I'm looking for. So if I need to solve for L now, I need to take this from log form to exponential form. So we're going to use what I love to call the swing rule. Getting rid of an ln is as easy as swinging the base over to the other side. E is the limit. So as x approaches infinity, 1 plus 1 over x to the x goes to e. And that is exactly where e comes from. It comes from a limit. How crazy is that? So there you go. All right, so this next one, try it on your own if you think you want to, or hit pause and come back. All right, so I plug in 0. This is 0 to the 0. Fine. So that means I'm going to set the other side equal to L, because I don't know what else to do with it. Then I'm going to take the ln of both sides. So I have the limit as x approaches 0 is ln x to the x equals ln L. This comes down in front. The limit as x approaches 0 of x ln x equals ln L. This is now 0 times the ln of 0, which is negative infinity. 0 times negative infinity is indeterminate, so let's make this guy a fraction. The limit as x approaches 0 of ln x over 1 over x still equals ln L, just going to remind. This goes to negative infinity, that goes to infinity. Infinity over infinity, L'Hopital. So now I'm going to do L'Hopital. I'm going to take the derivative of the top and of the bottom. The derivative of the top, 1 over x. The derivative of the bottom, negative 1 over x squared. This simplifies to the limit as x approaches 0 of negative x. This, as x goes to 0, equals ln L. Turn this into exponential form, L equals e to the 0, which is 1. So 0 to the 0 approaches 1. All right, so long story short, when you have limits that go to 0 over 0, infinity over infinity, infinity minus infinity, infinity times 0, 0 to the 0, or 1 to the infinity, all of these are indeterminate. But if you can make it look like this, you can do L'Hopital. All right, that is it. I am done. I need a stupid joke. Stupid joke. Stupid joke is, what do cats wear under their pants? Diapers. Oh, I know it's not good, but it's stupid. See you soon. Bye.